Perfect. So tell me what is a good quality of a teacher? One, Chakravarti garu meer active ga unnaru okati pettandi chat lo. You can be the leader. You can put it to everyone. Attitude to teach. Okay, let me write it down here. Attitude to teach. I call it passion, right? That's what you mean by. Okay. Next one, student friendly. Jane. Oh, only one. You want agree teacher is very engaging. Engaging. Okay. Attention. Engaging and holds the attention. Okay, perfect. Who said that? Chakravarti garu, you cannot give so many answers. Only one. Only one allowed. The faculty to have a chance. Okay, Jntuk is very active all the time, so are others. Let's put a couple of more. You should be able to type fast. We should beat Chakravarti garu. He has already typed 3. How about caring? I'll put 1. I should get 1 in, right? Okay. I need 2 more. 2 more from faculty and 4 from students. Need 2 more. 4. 2 more from faculty and 4 from students. 2 more from faculty and 4 from students. Okay. First 2 from faculty. Or James. Excellent. Put it right away. Vasavi, how about Vasavi? Give me 1 more. Qualities of great teacher. I just need 1 more. I just need 1 more, guys. Wow.
Sir, can I give now?
The last one. The last one I'm finding it difficult. Huh? You're all great teachers, I know. Great teachers, I know. They're all teachers. You're all in the chat. Okay. Oh, motivate. Perfect. Motivate. Perfect. Excellent. So, one second. It became 1 second, guys. Okay, can you hear me now? You should be able to hear me now. Okay, you should be able to hear me because I think somehow I don't know whether I myself. Whether I muted myself. what I was saying was, yes. So what I was saying was, those are all great quotes from the faculty. What I was saying was, great quotes from the faculty. He's a super smart kid, won't say that in front of him. And he's a fantastic programmer. He's a straight A student in Berkeley pretty much. Okay, A plus in analysis of algorithms. So I asked, how does this dynamic programming, how did you learn? And his answer was quite simple. He said, Papa, the only way you learn that is by doing it. That means you have to make your students program. The way you learn concepts is by programming. Remember when I started off the let's do some programming examples. So keep that in mind when we are learning dynamic programming. You how the let's do some programming examples. Mind when we are class, we'll do some getting some concepts at least. Now, what is yes, it's on B trees, the balanced trees, and then we did different types of tree structures and all that, right? You're right. Or post them in the community forum, and one of us will answer them. Okay? That way I don't want to take the time away from today's class, because we need to make some focus on dynamic programming. Okay. Jntuk Moocs had some questions on that post replies, and I will also post my responses there. Okay. So what is dynamic about programming? It's almost like, mute yourself please. It's almost like if you say dynamic programming is the opposite of static programming. I don't know what static programming is, I don't know what dynamic programming is, but I'll tell you what they mean by that in this class, okay? Generally, when you talk about dynamic, we talk about some moving parts, something done on the fly. Like in the concept of operating system, we talk about dynamic memory allocation. What does dynamic memory allocation mean? While the process is executing in the CPU or a program, process could be related to a program, right? You allocate memory on the heap. That is dynamic memory allocation. Okay? But you don't quite have that connotation when we talk about this dynamic programming stuff here. Right off the bat, I should tell you. to tell you in the way they use dynamic programming, it's almost like we are looking at programming, right? We learned that at the very beginning of this class. It's all about efficiency, right? The term that we use is optimization. Right? We want to optimize the code algorithm in such a way it executes. Okay? So in order for a program to execute in the fastest possible time, a couple of things need to happen, right? The time complexity has to be reduced, right? If the time complexity is higher, then it takes longer. Of course, we also have storage complexity. We want to reduce the amount of storage. Okay? So the concept, when it was originally proposed by one scientist in the 1950s, he said, hey, these are some tricks that you can apply. Okay? Those are the glimpses that you would see in this chapter. Now, second thing, programming is science become tricks too. Today, very experienced programmers have difficulty doing dynamic programming. That's why it is an art. So, considering that your undergrads, on a scale of 1 to 10, your programming knowledge might be maybe 6 or a 7, not counting the geniuses in the class, okay? This is a difficult concept right off the bat. So I'm making it very clear to you. So if you understand only a little bit, you can enhance your learning by writing some programming, doing some programming. Okay, keep that in mind. Okay, we will go slow. I'm having some difficulty here. Okay, so let's remember the counting coins example that we did from eons ago. Let's revisit that. Okay, so I have an example of counting coins. So I have these coins 1, 5, 10 and 25 denomination. Okay, I want to arrive at 31. Okay, I want to get to 31 in the most optimized way. Okay, so how can we find the minimum number of coins? Coin set. How did we do it? Who remembers how we? Didn't we say in the greedy algorithm we always take the largest denomination of the coin, right? If you recall, and then take the next largest and so on, as long as you are less than or equal to the desired amount. That's what we learned, if you remember. Okay, that was the greedy method, right? The greedy method was take the highest denomination towards your goal of reaching the target. Okay, so in the case of greedy method, we took 25, 5, 1. Agree? Okay, so that makes it 31. Fantastic. Worked fantastic, right? And then have your paper and pencil ready when we are doing these things. Now let's assume coin 5 is not there. Not there. Okay? I remove coin 5. So if I remove coin 5, what is my denomination here? I'll have to do 25. Greedy method, right? Greedy method, take the highest coin. Right, I'm typing on the fly here, okay? Then I take the next highest coin. But next highest coin is 10. If I take it, I'll go beyond 31. So I cannot take 10. I have to take 1, 1, 1, 1, 1, 25, 26, 27, 29, 30, 31. Okay? So once I remove the coin, 5 cents or 5, unit 5. So this is what I get. So how many coins I got? 1, 2, 3, 4, 5, 7 coins. Right? Okay? Okay. Now, what happens? Is that optimal or not? Is that optimized? Is it optimized? It is not optimized. Right? Simple example, but powerful concept. Right? It is not optimized in terms of the number of coins because in the greedy method I took 25 first, but what if I calculate, do other ways of doing it? Some tricks I can apply, in which case if I apply the tricks I could have chosen 10, 10, another 10 and 1 equal to 31. So by not applying greedy method, by applying some other optimization technique, I was able to reduce the number of coins that I can use to come to 31. So do you see the difference? That is dynamic programming in a nutshell. Now, faculty members don't jump at me saying, no, that is not dynamic programming. For now, please take that as a definition. What we are doing is dynamic programming. In the essence of dynamic programming is optimization. Okay? I mean, I would argue the essence of programming is always optimization. I don't know why they have to. The people who have invented dynamic programming have to say it deals with optimization. Everything should deal with optimization, in my opinion. Okay, but let's assume what they said then. Okay, so it is all about optimizing. Now, what are you optimizing? Some objective function. Here, in this case, is minimum number of functions. Okay, obviously, most often we want to optimize the time complexity, the time it takes for the solution to come. Okay. Okay. Same thing. Now see the couple of other questions that I put there. If we add a coin 21 to this one, let's say I add a coin 21. Okay. Now if I want to come to 63, so in greedy method I would go with 25 first, then I'll go with 21, that makes it 46, then I'll go with 10, 56, okay, and then if there is a 5 I'll go with 5, that is 61 and 2 1-cent coins. But if I use a different method than non-greedy method, which we call it dynamic programming because of some tricks that we apply, we simply use three 21-cent coins and we get it with just 3 coins. Okay. So greedy method works most of the time, but it's not always optimal. If you look at the shortest path problem that we did, the greedy method worked just fine. Okay. So it depends on the context. Sometimes it may work and sometimes it may not work. Okay. So that kind of explains to you a little bit more detail. Okay. what we do here is, let's consider this example here. Somebody type something? No. Okay. So we are assuming the following denominations. Okay. And then we are using 63 cents as a goal. Okay. How do we arrive at that? Right? Let's look at the simple solution here. Okay. So we need 1 cent coin to begin with. Okay. You can convert the cent into paisa or whatever, right? It's some unit. Okay. So to make k cents, you can see the algorithm here, right? That means, let's say if I want 63 cents, if there is 63 cent coin, then that one coin is the minimum that is required. But we do not have a 63 cent coin. We only have these coins. Remember that. Okay. Otherwise, what we do is for each value I less than k, okay, find the minimum number of coins there to make I cents. Okay, and find the minimum number of coins needed to make k minus I cents. Okay, so by applying that recursively, we ultimately come up with an I that minimizes this sum. Okay, again, it is all written in plain English text. If you work out on a piece of paper, that will work. That is what you need to convince yourself after the lecture or during the break. Okay. Now when you do these things, as you can see, there are some problems with this. It's a recursive solution and requires exponential work, because as the k grows, if the denominations are much larger, meaning I only showed you 4 or 5 here, if that set, if the sample set grows, then this will take more and more time. That is what this says. Okay? But it can be done for small set of solutions. Okay? Now here is another way of doing it. Now notice one thing. The more you come up with solutions which have some tricks, okay, I call them tricks, the more complicated it looks in terms of understanding. Unless you program it, you would not be able to appreciate that. Okay? So what does this solution say? We can reduce the problem recursively, okay, by choosing the first coin and solving for the amount that is left. So in this case, what we are saying is, we'll choose 1 cent coin first. Okay, there are two aspects. We are choosing one coin and solving for the amount left. Okay, so you're starting with 1 cent. You're solving for 62 cents. And you're doing it recursively. Remember, it's the same thing. The algorithm is the same, but you're applying recursion to the balance. Then you choose 5 cents. Once you choose 5 cents, then you do the best solution for remaining cents. Okay? If you're choosing 10 cents, you optimize for 53 cents. See, this 5 cent plus 58 is 63, 1 plus 62 is 63. See how you're choosing one each of these denominations, and you're choosing the best solution for the remainder. Okay? So by doing like this, what you have basically done is, you have 1, 2, 3, 4, 5. You're choosing the best solution from among the 5 given above. So we have solved the problem by eliminating 62 recursive problems. We solve 5. Okay? Now, when you program it, you will again break down 62 and so on. Okay? You will figure that out as we go along. Okay? But what I want you to visualize is, the greedy algorithm is not the only way to solve a problem. There are other ways of solving problems to optimize. Okay? That is the essence of this discussion here so far. Okay? Now, here is a dynamic programming solution. Okay? So you solve first for 1 cent, then 2 cents, then 3 cents, up to the desired amount. Okay. Now when you are solving that, you are saving each answer in an array. Okay. Again, listening to a lecture is not enough. These things you have to literally do it. I keep emphasizing that. Okay. And then for each new amount n, you have to compute all the possible pairs of previous answers which sum to n. So let's look at that. What do those two bullets mean? Okay. I'm showing you an example here. Our goal is to come to 13 cents. I'm getting some static or echo. Is everyone muted? Let me look at the participants here. Jntuk, I'm muting you. It could be static from you. Okay. Again, I'm not in a rush to rush through this one, students. Okay. I'll go slow for you. So here is dynamic programming. What does it say here? So you are going to, our goal is to get to 13 cents. Okay. So you're first going to solve for 1 cent, then 2 cents, 3 cents, up to 12 cents. Okay. So when you're solutioning for 1 cent, then you have to figure out a solution for 12 cents. When you're solutioning for 2 cents, 11 cents. You get the idea. Okay. Once you do this, you choose the best among them. Okay. Does it look different? Let me ask you the show of hands. I see a bunch of students in Jntuk there today. Show of hands. Do you agree that this solution looks different than the greedy algorithm? Yes, right? I said show of hands, meaning you have to raise your hand if you agree that this looks different from greedy algorithm. And I can see Jntuk students sitting there. Is it a dumb question? You're not raising your hands, or you're not able to hear me? Obviously it is different, right? Now, how on earth? This is where I say, right? This is why I say this type of programming is more an art than science. How on earth you can come up with something like this based on some programming knowledge? You cannot, right? This is all about thinking, right? Some scientist was able to come up with a smart answer how to do these things. Okay. I don't know if you guys grew up solving puzzles. This is kind of like almost like to me solving a puzzle. Okay, I got some brilliant idea, and it worked, and then I became famous, right? Like that. So by doing it like this, if you ask me the question, how can you come up with this? I cannot answer that. No one can answer that. It just happened. Okay? Now, so again, I'll repeat one more time with respect to this one. So what you're doing, you're taking an amount, you're solving it for all the 1 cent, 2 cent, all the way up to that amount, one less, right? And then you see the solution for 1 cent plus the solution for 12 cents. So this comes to some X number of coin, right? And then solution for 2 cents, solution for 11 cents, some Y number of coins. So out of all these possible solutions, there is one optimal solution. That is what dynamic programming is. Okay. Let me proceed here. Okay. Here is an example. Okay. You have 1 cent, 3 cents, and 4 cents. Okay. There is only one way to make 1 cent because one coin, right? Remember, we go all the way from 1, 2, 3, and so on, right? Okay. Now to make 2 cents, you can choose 1 coin plus 1 coin, right? 1 cent, 1 cent. To make 3 cents, you can use a 3-cent coin. To make 4 cents, you can use a 4-cent coin. Now, to make a 5-cent coin, what do we do? Remember, we said go from 1 and choose the remaining, right? Remaining is 5 minus 1, right? Because in total you want to make 5 cents. So what is the optimal solution for 4 cents is what you're saying. Next, choose 2 cents, 5 minus 2, 3. Make an optimal solution for that. Okay. Now if you choose 3 cents, the other one would be 2, right? 2 plus 3 same as 3 plus 2. So we got the full solution set here between the first 2 bullets. Okay. So you know how many coins are required in the first case and in the second case. So the first solution is better. Okay. That is my pass 1 of explaining that. I will go to the same thing a second time. Okay. All this example is doing is following this algorithm here, right? If you go back to the algorithm here, the first 2 steps, right? So you're solving for all of these things up to the amount that you desire, and then you choose the best solution among them. So solution for 1 cent, solution for 2 cents, solution for 3, and so on. Okay? So when I go here, so I have these 3 coins here, okay? And then I want to make 5 cents. How do I get to 5 cents optimally? So applying step number 1, I said, okay, solve for 1 cent plus the remaining. Remaining is the balance to make it 5. That's why 4 cents here. Then the second one I say solve for 2 cents and the balance. Okay. Why did I not write here another one as 3 cents? Because the balance should be plus 2 cents. 3c plus 2c is the same as above, right? Correct? So it does not. And then if I do 4c plus 1c is same as the top. So these 2 are same as this. So I can stop at these 2. I don't need to use these 2. Okay. So now I know how to get 1 cent because it's 1 coin, it's listed there. I know how to get to 4 cents because it's listed here how to make 4 cents. Okay. So same thing, I gave you one more example for 6 cents. Okay. Now JNTUV, raise your hands if you understand that. I'm seeing JNTUV picture today, so I'm perfect. That's good. That gives me confidence. Now people who did not raise their hands, give me one good reason as to why you did not understand that. I expect 100% of you to be raising the hands, right? But it's okay. Sometimes it takes more time. You are probably like me. I never understood whenever I learned it from a professor. My apologies to all the faculty members for saying that. I'm more of a self-learner. Only 2 teachers inspired me where I learned something nice, right? But those of you who did not raise the hand, when you do the group exercise, go talk to the guys who raised the hand and learn from them. Okay? Okay, great. So you see the dynamic programming simple example here, how we did that, completely different from greedy method. Okay, let me pause here for a second. The faculty members are welcome to add their comments to clarify the concept. If any faculty member has a different perspective to explain the simple example, please unmute yourself and explain. That way I can also listen to you. Okay, I'll monitor the chat. If they want to speak, they can. Okay. Now let me. I'm not able to see the video of JNTU. If people are wondering why I'm partial to JNTUV today, the only video that I'm seeing here is JNTUV today. Now, yeah, that's the only video that I'm seeing on my screen. I cannot see, now I see SVCW, Vasavi, I don't see Jntuk Kakinada. Let me ask Vasavi. Oh, where did Vasavi go? Somebody came there. St. Anne's. SVCW. Raise your hands if you understood the concepts. I can see your video. Cameraman, you can focus on them so I can see them better. Okay, perfect. Makes me feel fantastic as a teacher. This is, believe me, I spent a lot of time preparing for this class because this is such an important concept. Tough, but I would get great satisfaction when most of you understand, right? Okay, Vasavi, I can't see video. Still, I cannot see any videos. When I see the video, I'll ask them to raise hands. For those of you who I cannot see the video, you can raise your hands anyway because it will be a good exercise. Okay? Remember I told you we used to do some stretching exercises in my other class. Now, true to the spirit of what I said in the beginning, okay, here is a piece of code to implement what I just said. Okay, so when I post the slides there, go ahead and do it. This is a very easy example, very easy to program. It should not take you more than, if you do it as a group of 2 or 3 people, maybe 2. You can easily program it in any language that I believe you all learned Java. Of course, you have to put all the classes in the main and all that stuff, right? So, but here's the piece of code to implement that. Okay? Okay. Now, I gave you 2 or 3 different algorithms there, right? So some analysis there. You can convince yourself after the class when you read the notes. And if you have questions, you can always put it in the community forum, and we'll justify it. Okay. So the first algorithm had a branching factor of 62. Okay. If you take the average, it will be over that. Exponential time, useless algorithm. Okay. Small data sets, it works. And the second one has a branching factor of 5. Remember, there are 5 paths that we had to take. I showed that. Okay. But it's still exponential time. When you come to the trick that we show, for optimality. Okay. What is the condition here? Condition is principle is if the optimal solution always contains optimal solutions to all subproblems. That is the key condition. It is like a if and only if condition. In maths we talk about if and only if, right? So it's almost like an if and only if condition, right? So you cannot have an optimal solution where the subproblems are not optimal. That cannot be true. And it's a one-way relationship. I'll tell you what I mean by that when we go down here. Okay. So if you look at the problem here, okay, where you want to make n cents with the fewest number of coins. Okay. If there's an n cent coin, yes, you get 1 coin and you're done. Okay. Otherwise, you break that n into 2 non-empty subsets, right? Because you're going to choose some coins from different subsets. So the 2 subsets, we call it n1 and n2. Okay. Now, if either of these things can be made with fewer coins, then clearly n cent can be made fewer. Then clearly n cent can be made fewer coins. That's why the solution would not be optimal, because the whole idea is when you break it down. Sorry, I'll explain it a couple of times. Give me a second. if this subset is not optimal and both the subsets are not sense, and the other branch like this, okay, is that the reason is there is a 10-cent coin, right? Okay, so the way you break it down into subsets with optimal solutions is what will give you the 13 cents. Now, is there any rule? Are there again, as I said, dynamic programming it's like an art, right? As I said, how do you break down the objective function into two subsets which give us an optimal solution? That is what intellectual brain power is an easy way to assign. One of the things I need to emphasize here is, see this one here, I put it in red here. The print, if you have an optimal solution to all subproblems, then you can combine them to get an optimal solution. So just because you broke it down into subproblems which have optimal solutions, right? That you can get an optimal solution at the top. It is not like A implies. Remember, in maths we learn A implies B does not mean B implies A. Okay, it only. So it is, again, that is all the theory, right? Now, how many of you truly understand all this? I doubt it, right? Unless you do it, you would not be able to appreciate this, right? So let me repeat one more time here. Okay? Going from the top, an optimal solution always contains optimal solutions to all subproblems. Okay? Going from the top, for P. At the top, when say A is the optimal solution, all the subproblems are optimal. Okay? But if you are going the other way around, where you say I got all the subproblems optimal, it does not mean combining all the subproblems will still give you an optimal solution. It's like a concept, it's a mathematical concept actually. A implies B and does not imply B implies A. Okay? That is what this is saying. This was here to see if anyone has questions that I can answer before I have another example. Let me check here. Yeah, I'll go back to the same thing here. See this one here? See this one? To bring out that optimality does not say 7 cents is this is optimal, right? So you are saying for 13 cents, so there's an optimal solution of 7 cents. And the C1, total number of coins is 1, 2, 3, 1, C. And then you have to pay more attention to dynamic programming. More attention to dynamic. Although more important, mathematical equations like binomial coefficients. Later on, we'll see matrix, an example of matrix multiplication. Okay, So dynamic programming comes in very handy there to reduce the time complexity. Now when you talk about optimization, the main thing is, to summarize, is to be able to divide a problem into the right sub-problems. When I say right sub-problem, that means they should yield the overall optimality as opposed to optimum at the sub-level. Okay? And an example to demonstrate that here is the simple example here. When I break down 13 cents to seeing an optimal solution, whereas when I am able to break that 13 cents into 11 and 2 subsets, then I am able to get an optimal solution. So this example shows you that breaking that into the right subsets is key. Okay, now let me pause here. We spent over an hour already on this. Time for my 5-minute break, right? This is the stretch break for all of you for 5 minutes. You can get up, stretch, do some yoga, do whatever, but please do get up and stretch. Generally, I don't believe in continuous sitting in a chair like that. I'll go get my cup of tea and I'll be right back. Time now is 10:23. In 5 minutes, I should be back. Okay? Putting you on pause here for a second. Okay, 5 minutes starts now. I am back. Let's see. I do see Chaitanya video now. I see Jntuk video. I see SVCW video. Vasavi and Guide I don't. Jntuk Kakinada, I see the video. Okay. Jntuk Kakinada, raise your hands. That way I can see that you are raising your hands. There you go. Thank you. Perfect. Okay. We continue to work on today, okay? In the group exercise, we'll do lecture for another a little bit more time, and then there's a pretty involved group exercise that I want you to do in groups, okay? Okay. So, I don't know why this slide I kept it here, but let's look at this one here. I think I may screw up the explanation, but I'll give it a shot here. So, just in case we think that dynamic programming is that is a panacea or a solution for everything on earth, this example shows that sometimes dynamic programming approach does not work. Okay. So just because it is a great one, doesn't mean it works in every situation, right? So here is a small graph that you have here, A, B, C, D, right? With certain times, the 1, 3, 2, 4, they can be units of time, how much time it takes to traverse from one node to the other node. It could be some other effort indicator, right? So if you look at the long here, meaning a path that does not contain a cycle, that's a simple path, is A, B, C, D, right? You go from A to B, B to C, and C to D. Okay. Now, the reason why, if you are trying to do it with dynamic programming approach, you will see that it violates the principle of optimality. Because if you look at this subpath from A to B, remember the goal is to find the longest simple path, right? If you look at the subpath AB, that is not the longest simple path, because you can go from A to B via C, which would make it the path as 4, right? Not the 1. Okay. So obviously it is not satisfied. The principle of optimality is not satisfied. Optimality is to reduce the time it takes to go. So it violates the principle. So you really cannot solve this problem using a dynamic programming approach, because you cannot. The idea of optimization is reduction, but here you want to do the opposite of that. So you cannot really apply the dynamic programming approach there. Another great example of dynamic programming. Okay, remember we talked about the 0-1 knapsack problem, right? Where a thief getting into a house, he has a knapsack, and he can steal some stuff based on certain conditions, right? So when we looked at the greedy algorithm, we came with some approach. I don't remember how we did that. But the idea here is he can carry 25 pounds. His backpack, he can only carry 25 pounds. We also said that he cannot break the items into all or nothing, right? Meaning you either take it or you don't take it. If it is like powders and things like that, yeah, you can in theory take half of the powder and things like that. But here the assumption is you either take the full item or you don't take the full item. And each item has weight and value, right? That is the knapsack problem that we discussed when we did the greedy algorithm. Right? So obviously you want to steal in such a way that you want to maximize the value of the loot. Okay? So you cannot exceed 25 pounds, but if you count all the money value of it, it should be the maximum. So how do you do that? So it has been shown that the dynamic programming algorithm works very well there. This is where the mathematicians and the computer scientists talk about that. Imagine asking the thief to apply dynamic programming principles to come up with that. How ridiculous it will be. The thief doesn't have time to think. But from a mathematical modeling perspective, it makes sense, not from a practical perspective. Okay? Because it's very similar to the coins problem, right? So here we are talking about contrast. You have the optimal solution. The optimal solution is maybe less than or equal to the weight limit. Okay, so you can, and in my classes here, typically students write programming exercises around this. Okay. Now here are some comments related to dynamic programming. It works for dynamic programming. It works on, and then solve a problem in a bottom-up approach. You don't need to resolve that problem again. Okay, that problem, the solution is there, and the program can use that solution. Okay. Yes, key, as I warned you in the beginning, it is not a science, it is an art. Thousands and thousands of experienced programmers still have difficulty programming using the dynamic programming principles. Okay. But it's not so intuitive. Okay. And it is only applicable to problems where the principle of optimality applies. Okay. And then wherever you have exponential times, when you do your algorithmic analysis, here is one good rule of thumb. Even while I'm speaking, I'm getting this idea, right? The basic big O analysis anyone can do. That's very what the primitive of the steps are, and based on that you can compute, right? Order of log based n or 1 or n squared, n cubed, n factorial, any of those things, right? So when you see those big exponential times, maybe that is where you can pause and say, hey, is there any dynamic programming idea? And programming ideas that I can use to come up. Any good programmer, by the way, does do some big O notation. Once they come up with an algorithm, it takes only 5 minutes for them to figure out what the big O is, right? And then in big O, you're not trying to be exact. The aim is always to go for a log based. As long as it's a log of n or 1, it is a good algorithm, right? So the moment it gets into the higher ends factorial stuff, then it's exponential, then you try to look for a better solution. Okay. Now here is a summary between greedy versus dynamic programming. Okay. So in the case of a greedy method, it is making its choices in a serial forward fashion, meaning once you make a choice, go forward. Remember, we did the shortest path, right? You choose between two different vertices. You see which is the shortest path, go to the states is not maintained in greedy algorithms. That's why you never look back. Whatever choice you made previously, you will not revert back to that. Okay? Whereas in the case of dynamic programming, you're trying many different possibilities before you choose. Okay, one is it's like in the case of shortest path, say, hey, let me go to the shortest path to the next node. Once you go there, you don't worry about the previous node, right? That is how you progress. That's why it's called going forward serially, right, in a forward fashion. Whereas dynamic programming, before you take that step, you're looking for all possibilities, right, before you come up with an optimal set. Okay. Now the last 2 bullet points are from a theoretical perspective important, right? In the case of greedy, there is no litmus test, right, whether the greedy method will lead to an optimal solution or not. Most often it does. With experience you know whether it works or not, right? But there are cases where it may not lead to an optimal solution. Whereas in dynamic programming, because we have this principle of optimality that has to be satisfied, then we know that if you are able to come up with the complete algorithm based on satisfying the principle of optimality, the overall solution will be optimal. A couple of more. Both in divide and conquer, we split the input into parts. Remember when we did the binary search or the sorting and all that, we always split that into different subparts and then we worked on each of the subparts. Same thing we do in dynamic programming too. Okay. Now when you split that, you have to figure out what is the right split points, right? You have to say, okay, these are the split points that I would use, and then you try for all those split points and see which split point is optimal in dynamic programming. Whereas in divide and conquer, sorting algorithm where you're searching for a key, you're always splitting in the middle, right? That's why it's called a binary search. Every time you split, you're reducing the state space by half. So we know exactly where to split in divide and conquer approaches. Whereas in dynamic programming, you have different ways of splitting. I gave you an example of the coins, right? In 13 cents, you can split 7 and 6, or you can split 11 and 2. And then you calculate it for all those splits and see whichever one is the most optimum, you will choose that one. Okay. So these are some differences and similarities between divide and conquer and okay. So here is a talking about the principle of optimality. The shortest path problem that we did, it always satisfies the principle of optimality. Okay, there is some proof here. If you let you convince yourself as to why that is true. That is the second bullet. Okay, and then in the case of longest path problem, where I gave you an example on the previous slide, that is one example where you can prove. This is proved by contradiction. All know a ring, right? A ring topology A, B, C, D, E. So it does not have a direction. Okay? So if you look at the longest path from A to D, you go A, B, C, D in a ring, right? But to go from B to C, you can always go backwards, right? That means meaning you can go from B to A to E, E to D, and D to C. Okay, so the subpath in the longest path is not necessarily a longest path. So it's not an optimal solution there. Okay, so some interesting tidbits there. Now, the question then becomes, right? How do you go about doing dynamic programming? So depending on which book, which author you pick up from, they list some steps. Okay, but the essence of the steps is you have some kind of a notation that you want to express the solution in sub-solution. Most often it looks like a mathematical notation. Okay, you have to prove that the principle of optimality holds. Okay, and you develop a recurring relation, meaning that shows the recursiveness, right? And you're going, basically you're dividing the problem, right? So you need a recurrence relation. Okay, and once you come up with the recurring values, you then write an algorithm to compute that. Okay. Again, theory, right? Once you do some practice problems, until then you would not appreciate what all these things mean. Okay, here is an example. Okay, we'll do this example and then I'll give you one example is at the end where I want you to do some hands-on also. Okay, here is an example of a matrix multiplication which lends itself very well for dynamic programming. Okay. So you have an input as n matrices, right? Now how many of you, show of hand, see Jntuk Moocs picture? Raise your hand if you remember matrix multiplication. Okay, some of you, okay, all of you remember? Oh my god, you're all geniuses. Jntuk, do you remember matrix multiplication? Raise your hands if you do. Okay. Wow. I'm teaching this course to a lot of geniuses here. Others, if I am not calling you out, that means I am not able to see your video. It's not like I am partial to them. I know that SVCW always raises their hand, but I can't. All of you remember. So let me be honest with you. I don't remember matrix multiplication. In order for me to, it's like this, you know, the more you know, the more you, the less you know, right? You ask me about information security and things like that. I'm the king of that field right now, or one of the. I'm pretty good at what I do. Okay. You ask me about math, trigonometry, matrix, and all that. I have no idea. So literally, I had to go and then review my matrix multiplication skills before the class today. It doesn't mean I don't know math. I just don't remember any of these things. Here is the example of matrix multiplication. Again, classic example for dynamic programming. So you have different matrices, right? Now you want to compute the matrix product, meaning multiplication. Okay. So I'm giving you an example of two matrices here, right? And then you want to multiply. So what is the matrix that you get here? Is it a 2 by 2, 2 by 3? What type of matrix you get on the right side? Put it in the chat for me, please. And this is a 2 by 3, and this is 3 by 2. Remember, when you have a matrix, when you have, like, why am I not able to write here? Because the text is, if I do. So one of the theories that we have is when you have A by B, the second matrix has to be B by C, right? B times C, right? This B and this B, they have to match, right? The number of columns here, right? So when you do that, you get it. Oh, right. I don't know why I was typing. I need to type here. I'm not able to go there. So you get a 2 by 2 matrix. Thank you. Okay. So what are the values of the 2 by 2 matrix? You are all busy working there. It's some values, right? I think I already listed there. So how do you do the matrix multiplication? Here is the matrix multiplication, right? Follow this example carefully, yeah, because this is part of. To me, I get these are the values that I get in the 2 by 2, unless I screwed up my math. So you take the first row. For those of you who forgot, like me, I don't trust that all of you remember, okay? Some of you would have forgotten. So the way you do that is you take row 1, 2, 3 and then you multiply column, right? And the way you do that, corresponding numbers, 1 times 7, 2 times 9, 3 times 11. That is 58. That goes in here. Same one row, same row 1, column 2. Right. Now, how do you compute the cost of matrix multiplication? Either my numbers here that I am showing are wrong or what you are typing is wrong. But that's a moot point anyway. My math, I don't trust my math any longer. But you get the idea. The way we have to multiply is row 1, column 1, row 1, column 2. This is the dot product, right? The dot is the dot product. Okay? And I showed you how to multiply also here. 7 plus 18 is 25. 25 plus 33 is 58. Wow. It's incredible, huh? How I'm getting different answers here, but that's not a big deal, okay? I think what I have is correct, but you can verify. Okay. Now, how do we compute the matrix multiplication? This really brings out the essence of dynamic programming. Okay. So, there are different ways, right? Basically, if you go back to our fundamental principles, what do we have here? We have a whole bunch of multiplications and then we have a whole bunch of additions, right? That's what you see here. 1 times 7 is multiplication and you have certain additions. Multiplications than additions. Okay? Even if you see each line, how many multiplications are there? There are 3 multiplications, right? Whereas only 2 additions. Okay? Now remember, in our big O notation and all that, we take the largest factor and ignore the rest. So if you really apply that here, you will ignore the additions, you will see all the multiplications. Okay? So that gives you the number in terms of a quantifiable metric or a number to see how much matrix multiplication costs. Okay? So if you go to the next slide here, basically do is, here is the example, the cost that I gave you. If you have 2 matrices with dimensions, remember Q and Q have to match, and then C is your multiplication of A and B, and the dimension of that is P by R, right? That's how you came up with the 2 by 2 matrix there. Okay, and each element, it shows how to compute. Okay, and if you notice, each element, it has n multiplication, n minus 1 additions. Okay, if you go back to the previous example, how many we have each element? 3 multiplications and 3 minus 1 additions, 2 additions, right? That is what this says. Multiplications and n minus 1 additions. Okay? Now multiplication, you know, is always more expensive than addition. That's rule number 1, right? So we know that it's one of those facts, axioms, right? Multiplication takes more CPU cycles, okay, than a simple addition. So we count only the scalar multiplications. Okay. So when you do that, you will notice that the total number of multiplication will be P times Q times R times. So what is P? P is 3 here in a 3 by 5, right? And then you have there, right? So in the example that shows here is when you have 3 different matrices, if you have to multiply them, would you multiply A1, A2 first, followed by A3, or would you multiply A2, A3 first, and then multiply A1 with that? You understand the question? Okay. So you know how to calculate the matrix multiplication. The big formula basically is to do AB, mean basically to multiply that, you get see. Do I have whose hands do I, whose faces do I see? Today the bandwidth is really bad. I only see Jntuk. I see Chaitanya. Chaitanya, raise your hands if you understand this part. How many multiplications, how we calculate? Okay, perfect. Thank you. Okay, Jntuk, raise your hands if you understand how many multiplications are there. PQR, do you understand this step? How we came? This is I am asking in Jntuk. Did you raise your hands? Okay, one person raised the hand. All of you go ask him how he understood and you didn't understand. Example, if you, and I erased it here, that's all I did. If you carefully study how many multiplications are there are 3 here in the top, right? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. That is 12. So if you look at the formula here, if you plug it in, that should match. Okay, so this is the formula. See, you all know matrix multiplication, but you never thought about how many steps, how many times each element is being multiplied. So now you are getting into an analysis. Number 2, you are eliminating the additions, because in the overall scheme of things, multiplication is much more expensive than addition. Goes back to standard computer theory, right? How the bits have to be manipulated, shift left, shift right, and all of those things come into play. Okay, so now when you do that, if you compute this one, it comes to PRQ when you have 2 matrices, PQ and QR. You just take the dimensionality of the first 2 and then the last one, R of the second one, you get that. So now when I give you an example of A1, which is a 3 by 5 matrix, meaning 3 rows. So if I ask you this question, which one is better, whether doing it this way or doing it this way, you should be able to tell me what is the value of the multiplication here and what is the value of the multiplication here, right? So can somebody put it in the chat? What is the value of A1, A2, A3? Just apply the QR, right? Whoever puts the answer there, I'll take that as the correct answer. Remember, this is Q is 5, that's 3 times 5, 15 times 8, right? That is 120. So A1 and A2 would be 120. Did I get it correct? Okay. Times A3. So this resulting matrix is what? 3 by, what is the resulting matrix? 3 by 8, right? Correct? So then the next one would be 3 times 8 times 2, 20 plus 48. Right? That will be 168. Got it? Did you get that? Can somebody verify whether I did it correctly or wrong? Right? So all I am doing is multiplying, getting this multiplication steps, right? That is 120, and then whatever the resulting matrix is, which is 3 by 8, and then this matrix. So 3 times 8 times 2 is 48. So 120 plus 40 is 166. Do the same thing for here. You do A2 times A3. When you do A2 times A3, now the resulting matrix is 5 times 2, which is 10, and 3 times 5 times 2, 30. 80 plus 30, which is equal to 110. So in one case I am getting 168 multiplications, in another case I am getting 110 multiplications, right? So which is the right answer then? The right answer is you want to multiply A2 and A3 first, then you multiply that result with A1, because it results in less multiplications. And they are tentative. They are saying, should I be nice to the professor and raise my hand to make him happy, or should I not raise my hand and make him unhappy, right? Simple math, guys, right? Remember, professor can make a mistake. Students cannot make a mistake. Okay? Jntuk, do you understand? Raise your hands about the steps, multiplication step. I see a lot, yeah, some of them raising the hand. Others, no problem. You just need to think through a little bit. Remember, I told you it takes time for you to understand these things. All you have to do is, during your lunch break, spend 10 our behavioral psychology is when you are given A, B, C, left to right, we think from left to right. You say, okay, let's do A, B first, then we'll take that result and do B, C. How many of you have done that in exams? Be honest. 99% of us would have done it in the exam like that. Okay? If we knew dynamic programming, we would have multiplied dynamic programming. We would have multiplied the other two first, and then did BC first, and then did it with A. That would have saved us a lot of time, right? Even when I'm doing it manually. Okay? So this is where the dynamic here. But imagine if you had many matrices where you have to multiply. How can dynamic DP design approach help us? Okay. There is some theory here. Okay. How you compute the cost. Okay. Not really relevant in this class unless you want me to go deep, but I put some slides in there. There's a complete mathematical theory, and then ultimately when you review these slides, and I'm not going through that slide now, I'm just showing you what is there. I'll put it in the community folder. You download it, and then you in that equation, or we understand it. Okay, one of the faculty members who is much stronger in math at the moment than I am can explain it. Okay. Okay, so what did we learn here? What we learned here was one good example of dynamic programming where it comes into play. It is just not about simply multiplying arbitrarily. By applying certain techniques like this, like as this matrix multiplication shows, we can optimize the solution. Optimizing meaning reducing the amount of time. And the way you reduce the amount of time here is reducing the amount of steps here. The difference between 168 and 110 is what? You see 110. In today's world, it's all big data, right? Big data means millions and millions of records, and you will do a lot of joins in tables. You know that, right? When you write SQL queries in your database class, you would have learned we join tables. Now, when you are joining tables, it's a Cartesian product, right? What is the right way to join the tables is absolutely critical. So you are basically applying dynamic programming principle to solve the problem. Okay, so it is basically there everywhere for you. Okay. Okay. So much for preaching on that. I will stop. We covered. Convince yourself about some theory that I gave in terms of mathematical notation. I'll be the first one to tell you, even I would not know the mathematics. In order for me to explain this mathematics, I have to spend an hour drawing everything on a piece of paper. Okay, but we'll do it. If necessary, we'll do it. Okay. Then somewhere here, I showed you an example how for certain values of n, how you build this table. Okay, this is for a A4 matrix. There A1, A2, A3, A4. Map this to this one. Okay, then you will figure out that to multiply these 4 matrices, the order in which you need to do that is this. So I gave you a complete example of that. Okay, you have to do some little bit of homework to review the slides and do it. Okay, after you are done, before you come to the next class, this is important. Before you come to the next class, forget the rest of the slides here. Okay, you are very welcome to look at those slides, but somewhere at the end, I put a problem that I want you to tackle before you come to the cover those slides in the next class. Okay, but I want you to do as a group, pick up your friend, 1 or 2 of them, right? Try to solve this problem. Okay, what I would be interested in is looking at some solutions. Okay, how you solve that problem. If you go to the next slide, you will see that. Oh no, it's right here. Okay, yeah. Basically, you want to read this problem and see what is the way you would go about solving the problem, because that forms the basis for some of the discussion that we are going to do next. Understood? Is there anyone who does not understand the homework? Two slides of theory. and then look at the problem that has been solved there, and then convince yourself that these slides, okay? I gave you the theoretical way of computing the cost here, okay? Look at that, review these two slides, okay? Ultimately, you need to understand that equation, okay? Once you understand that equation, and the way to understand the equation is by looking at the example here. You go back and forth between those two slides, okay? Some investment problem that I showed you. These are the two things I want you to review before you come to the next class. Remember, it's a collaborative effort between you and me to learn these things. It's not a one-way preaching, okay? Okay, that's it. Any questions, comments? Faculty members, if you want to provide any insights, further insights beyond what I said, please come to the microphone and share it with students. I used to have a faculty member, Tirmal Rao Garu. At the end of every class, he used to come and provide his own insights too. That was really fun. So, for the students. Questions?